Okay, so what about non-standard conditions? So delta G and non-standard conditions. Let's look at a reaction as an example to kind of explain why we're going to talk about this. So liquid water turning into a gas at 25 degrees. This has a delta G reaction of positive 8.5 kilojoules per mole. So this is a non-favorable, non-spontaneous reaction. But we know that this happens. If you set water out at 25 degrees, it will evaporate. So the liquid will turn into a gas spontaneously, favorably. We don't need to put in an effort to get the water to evaporate. The reason this is happening is because in real life, this is not under standard conditions. So, standard conditions are that the pressure of the gas is 1 atmosphere. Well, the entire pressure is going to be 1 atmosphere if we just set a cup of water out on the bench top. You would not want 1 atmosphere of water vapor in the air that you're trying to breathe. So, the actual pressure of water under standard conditions, it's quite a bit less than 1 atmosphere. Um, I've gotten this value from the appendix. We haven't talked a lot about vapor pressure yet, but this is what we're looking at. So the vapor pressure of water at 25 degrees, normal conditions, it's 0.0313 atmospheres, quite a bit less than 1. So these are non-standard conditions. We don't have 1 atmosphere. We need to adjust the calculation in some way to account for this. And the way that we do that is with this addition of an RT-ln-Q term. So under non-standard conditions, my delta G without a circle is equal to my delta G with a circle plus RT-ln of Q. You know Q, you love Q. You've missed Q because we haven't dealt with it in so long. This is the reaction quotient. It's the same thing. It is taking where we are and using those conditions to adjust the delta G calculation. So in our reaction, to find our non-standard delta G, we have our standard delta G, which is the positive 8.5 kilojoules per mole, plus RT. Notice the version of R that I'm using is the 8.314, and I have it as 8.314 times 10 to the minus third, so that my units match. I'm at 25 degrees, so 298 K times the natural log of, I've just got the pressure in here, but go back and look at the reaction and convince yourself that Q is just equal to the pressure of the gas. So when you work this all the way out, the result is negative 0.0856 kilojoules per mole, which, sounds super small. We could say it in joules. It's 85.6 joules per mole, if that makes it sound a little bit better. Either way, it's negative. So this is favorable and spontaneous under these conditions, which is what we observe. So when a reaction is at equilibrium, Q is equal to K, and delta G is equal to 0. So with this addition, we can manipulate our reaction so that we have a direct relationship between the standard delta G and the equilibrium constant. So the equilibrium constant, because it's behind the natural log, let's kind of analyze what this would mean for the delta G. So equilibrium constant less than 1 favors the reactants, right? Let's reorient ourselves to equilibrium. Less than 1 favors the reactants, positive delta G. So K less than 1, when you take the natural log of something less than 1, you get a negative number, and then you multiply it by a negative 1. K greater than 1 favors the products. You get a positive number out of the natural log and then multiply it by a -1, you get a delta G that is negative. So you can now, if you have standard conditions, find the equilibrium constant for a reaction. So I can ask you to just calculate the equilibrium constant for this reaction. So the only thing I know is 298K. It has to be standard conditions because that's the only way I know how to get there. And I just need delta G for the reaction. So I have options, right? You should get the same correct answer either way. I need delta G reaction for this. So I could either calculate delta H, calculate delta S, put them together, or I could use the delta G formation to get delta G reaction. Both are correct. Once I have delta G reaction, then I can relate that directly to the equilibrium constant. So if we give this a try, 2 times the product minus 1 times the reactant, my delta G value is positive 2.8 kilojoules. My delta G reaction is equal to negative RT ln of KEQ. I have everything except for the KEQ. So what I'm going to do is rearrange this before I even start so that I don't have to try to get stuff out of the natural log while there are other numbers around. So if you rearrange this, KEQ is equal to E to the negative delta G over RT. So E to the negative 2.8, this time I've put everything in joules, so negative 2.8 times 10 to the third, divided by 8.314 times 298. The result is E to the negative 1.13, which is an equilibrium constant of 0.32. And we can see if this makes sense, right? Does that equilibrium constant make sense? It's less than 1. So it's a small equilibrium constant. My reactants would be favored. That should correspond to a positive delta G, and it does. It goes with the positive 2.8 kilojoules for delta G.